Should I get started? Yes, okay. Hi everybody, I'm Stefano Ermon. I'm an assistant professor with the computer science department at Stanford. I'm also part of the Woods Institute for the Environment, also at Stanford, which is kind of the umbrella organization where a lot of the environmental research at Stanford is happening. And so today I'm gonna be talking about some of my research on using AI, machine learning, and deep learning to address problems in sustainability, in particular poverty and agriculture. And the idea of this talk is that it's going to be like tutorial style, so there's not going to be a whole lot of new research ideas, but it's going to be more on sort of like introducing some basic approaches, where to get the data, what kind of problems are interesting in this space. So, you know, like if you have any questions, please feel free to interrupt me. That's the whole point of this lecture, is to try to, you know, teach you something, hopefully, on how these approaches might be useful for your research, or what kind of research problems you might be interested in pursuing. And so please do ask questions at any point. So let's get started. So as you heard from Bistra and from Jan before, you know, our society is facing some very important sustainability challenges. There is close to 1 billion people around the world living in poverty, hundreds of millions of people that don't have enough to eat. You know, there is climate change that's, you know, really threatening the survival of many societies around the planet. We're going to need new sources of clean and affordable energy, find ways to preserve biodiversity, and so on. These are very important problems. They've been recognized also by the United Nations. You can see here the 17 Sustainable Development Goals that were really identified by the UN a couple of years ago as being sort of like really the most important challenges that the international community is facing today. And clearly these problems are very important. They are also really hard to solve. And then one of the key challenges is that we don't understand these problems well enough. They are very complex. They occur sort of at a global scale. They involve multiple agents, multiple sources of uncertainty, multiple time scales, multiple spatial scales. And broadly speaking, we really don't understand these processes well enough. If you think about climate change, we don't have right now the capabilities of predicting what's going to happen in the future with sufficiently high sort of like certainty. You know, we don't understand the ecology of our planet. We don't understand you know, where poor people live in the world. You know we want to end extreme poverty, but we don't really understand how many poor people there are out there, where they live. You know, we know hunger is a big problem, but we don't understand agricultural systems in developing countries well enough. We don't understand how these problems are connected. I mean, we know there is a connection with climate change, how the climate is going to change, how it's going, that's in some way it's going to affect all of these problems and migrations and so forth, but we really don't have a good understanding of all these problems. And so that's kind of, I think, one of the key ideas of this computational sustainability field is really to see to what extent we can use computer science techniques, AI techniques in particular, to help address these problems. And in particular, I think one of the most promising ideas in this space is this fact that although these problems are really hard, as we've heard before in the previous talk, one good news is that we're really in the middle of a technological revolution where our sensing capabilities are becoming much better and better. If you think about, you know, from you know, this kind of satellites that we have in space that can take pictures of the whole world with very high spatial and temporal resolution. Think about the kind of capabilities that we have on our cell phones in terms of collecting data, storing it, communicating it very, very inexpensively. You know, social media. So there's a whole lot of new data sources that are becoming available globally. And these new data sets, they clearly contain a lot of useful information about these kind of processes that we're trying to model and control that are related to the sustainability goals. And I think one of the key challenges that we have today as a community is to try to find ways in which we can use AI techniques, machine learning techniques, computer science techniques in general, to figure out ways to use this data to obtain new insights that we can use to address these very important problems in a more effective way. And this is of course like a very broad research agenda, and you're gonna hear a lot of different ways in which different AI techniques, different computer science techniques can be used in this way. What I'm going to focus today in this tutorial, which is only 1 hour tutorial, so it's going to be relatively more focused on one particular way in which we can use AI techniques, in particular machine learning, to help address this problem. And I think this is a promising one in the sense that there are a lot of problems that can be sort of captured by this general idea. The idea is that for a lot of these problems, like trying to understand poverty or food security challenges or ecological challenges, a lot of the time we don't have enough data to understand exactly how things work. We don't have enough data to do research, say in the social sciences, try to figure out what are the environmental or societal or political drivers of the kind of variation that we see in poverty in developing countries. In the context of ecology, maybe we don't have enough data to understand bird migrations, or try to understand how the landscape is changing as an effect of climate change, or in the context of trying to figure out, understand better forest fires. Or there are a lot of kind of problems that we would like to understand better, but for which collecting data is expensive. Like going out in the field and do surveys and figure out whether birds are present or not, where poor people live, try to understand agricultural systems in developing countries is very expensive. On the other hand, as I mentioned before, there is a lot of new data that is becoming available through satellites, through remote sensing. And the nice thing about the data that we have on the left is that, well, it provides global coverage, so you can get data for every part of the world. It's frequently updated, so we can get new images every day, maybe every week, every 2 weeks. And it's cheap in the sense that the data is often publicly available. You can just download it, and or sort of like maybe it's expensive to put up a satellite, but after you've paid that fixed price, the data keeps coming in, and you can use it for these purposes. And so I think there are a lot of problems in this space where we can think about using machine learning techniques to predict these expensive measures that we might be interested, that are sort of related to sustainability problems, using these cheap data sources that are becoming available globally. So for example, we can use remote sensing to try to predict and understand bird migrations. We can use remote sensing data to understand how pastoralist tribes in Africa move around not affected by climate change. We can use remote sensing to understand where poor people live. We can use remote sensing data to try to understand agricultural system. There are a lot of these kind of applications where we can use these new advances in machine learning for turning these data sources, this remote sensing data, which is sort of there and it's available and it's getting better and better, into measures that we can use to inform policy and research in the context of these sustainability problems. So this is the kind of things I'm talking about. These are some high-resolution satellite images that you can get access today. As you can see, these are images taken from sort of like all over the place, but you can see that the resolution is pretty good. You can see a lot of stuff in these images. You can get a lot of information about the landscapes, about human activities, about settlements, about economic activities. You can see ships, you can see containers, you can see houses, you can see roads. So there is clearly a lot of information that is relevant to all sorts of sustainability problems. Now, these days, really the sensing is becoming better and better, cheaper and cheaper. This is a high-resolution video from space that is available commercially today. So this is not sort of like a military or like only available to the intelligence community. This is stuff that is commercially available today. You can get a video where you can see this power plant, and you can sort of see the smoke coming out, and you can imagine how potentially there is a lot of information in this kind of data to understand pollution and understand where it's coming from, how it's related to winds and the climate and all sort of things. And so that's kind of like one pushing force that is very exciting today, that the data is becoming better and better, cheaper and cheaper. And the other sort of force is that machine learning, and particular computer vision, is becoming better and better, which means that we can start to use all these data sources to estimate all sort of interesting things that might be relevant to sustainability problems. So since this is a tutorial, I thought I'd start by telling you a little bit about the kind of remote sensing data that is available today and that might be useful for your research. So when you think about remote sensing data, there are kind of 3 axes, maybe 4, that are relevant. The first one is the spatial resolution. Essentially, a remote sensing image is going to be an image with a bunch of pixels, and what you care about is what's each pixel. Basically, each pixel will correspond to a geographical area, and you care about how big that area is, because that basically defines what kind of things you can see in the image. The other one is the temporal resolution, essentially how frequently you can get an image for a certain location. And the third one is what kind of sensors you have on the satellite. You can get maybe visible light, like sort of like standard RGB, red, green, blue kind of images, but you can also get more. It's not just restricted to sort of the kind of images that people use in computer vision, where you only have like maybe 3 channels, but there is a lot more on these satellites. You can get infrared bands, near infrareds. You can sometimes have radar, thermal bands. So there's a lot of other kind of data modalities that are coming in from these sensors, and you might be able to use to infer interesting things. So there are several of these satellites and sort of like data products that are available today. Some are free, some are commercially available, so it means that you have to pay for them. The free ones, the main ones, I think there are 3 of them. The first one is Landsat. The resolution here is 30 meters, meaning that each pixel will correspond to an area of 30 meters by 30 meters. This is an old satellite. It's been there for a long time. It takes images every 16 days. So every location you can see it every 16 days. And it has sort of like the standard RGB bands plus thermal and a bunch of other bands. MODIS is another widely used data set that is available freely. Here there is the spatial resolution is much worse. It's 500 meters, meaning that each pixel will correspond to an area of 500 by 500 meters. And that clearly means, for example, that you're not going to be able to see cars, you're not going to be able to see people, you're not going to be able to see much at that kind of spatial resolution. The good news is that the frequency at which you get the images is pretty high. It's like 8 days. So you get a new image every 8 days, which means that if you're trying to understand a process that kind of occurs and changes at that kind of time scale, that might be a better data source for that particular problem. A more recent one is the Sentinel, which is by the European Space Agency. This one is relatively new, so it's like 1 or 2 years old, meaning that if you're trying to understand, say, changes in the last 20 years or 30 years, you cannot do it using Sentinel because there are only images available for the last year or 2. But it's a very good sensor. It's like 10-meter resolution, and the frequency is like every 5 days. So you can see it's much better than the older satellites, but you only basically have relatively recent images for that. Commercial products, these are things that you either have to pay or you have to talk to these companies to get access to the data. They are usually pretty open in terms of sharing data with people in academia. They are very much interested in developing machine learning capabilities. So if you develop an algorithm that can take their data and turn it into something useful, they're likely going to be very happy about it. And so that's essentially their incentive for sharing the data with you. So it's generally not that hard to get access to this kind of data. but it's a little bit more a pain than the free, publicly available kind of stuff. Here, the spatial resolution is much better. You can go down to even 50 centimeters or like 2 meters, so you can see a lot more stuff. You can see cars, you can see buildings, which are much better resolution. A very exciting one is Planet. This is a startup. It's in the Bay Area. They have a constellation of several hundred small CubeSat. These are like very tiny satellites that they are sending up into space using SpaceX, so driving the costs down. The nice thing about their approach is that they are able to provide right now global coverage at about 3 meter to 3 meter resolution, so reasonably good. And the temporal frequency is exceptional. Like they basically cover the whole world at 3-5 meter resolution every day. So you can imagine that with this kind of data coupled with good ML capabilities, you could do all sort of really, really exciting stuff, because you can see how the world is changing essentially on a daily basis. And sort of like the key question is, how do we turn all this data, all these images into actionable insights? How do we figure out what are the interesting bits out of this massive amount of data? As I said, this can be a lot of data, so it's not the kind of stuff that you do maybe on your laptop for fun. Just a back of the envelope calculation. Let's take Landsat. So as we said, say 30 meter resolution. It means that 1 pixel corresponds to an area of 30 times 30 meters. So let's say 1,000 square meters, just as an approximation. 1 pixel for, let's say, 1 band. Let's say that they're maybe usually stored as a 16-bit integer. So let's say 2 bytes per band, per pixel. Let's say that you care about, say, maybe something at the continent level, so maybe Africa. That's about 30 million square kilometers. So that's 30 million, and then it's a kilometer is 1,000 meters, so you have another 10 to the 6 square meters. So that's 30 times 10 to the 12 square meters. Now you divide by how big each pixel is, which is 1,000 square meters roughly. And you end up that you need something like 30 times 10 to the 9 pixels to cover, say, the whole African continent. Now let's say that each pixel takes you 2 bytes, and that's just for 1 band. That's about 60 gigabytes. Now let's say that you want 3 bands, just RGB, so just visible light. That's already 200 gigabytes. And then maybe you want 1 image per month, and you're already at 2.5 terabytes, roughly speaking. So you can imagine if you want more bands, you want more temporal sort of resolution, you want more images, this can get big pretty quickly. So the good news is that the data is all available on the cloud. So that's one way in which you can access it and process it without actually having to download locally. All these, the free ones, the free data sets I talked about before, are available for free on the Google Earth Engine. You just have to sign up, but it's free for sort of academic use. And then there are several options there. You can either do all the processing on the cloud using the Earth Engine platform, which is free, but it's sort of limited in the kind of things you can do. Like I don't think it's easy to train a model using Earth Engine. It's just not designed for that. It's designed for sort of like large-scale parallel processing of a lot of data, but not for AI or ML kind of applications. Option 1B, which I think is much better, is the fact that, as you know, Google has its own cloud platform, the Google Cloud, and sort of like the ML platform, and it's separate from Earth Engine, but they are connected in the sense that you can export data from Earth Engine to Google Cloud. So one option is to do all the processing on Google Cloud, which you have to pay sort of like the standard fees on the cloud, which is not too bad. Alternatively, what you can do is you can copy the data locally, which is actually what we do. just because we want the flexibility to do the training locally, and just that the prices right now for say, especially GPU instances on the cloud are still pretty expensive compared to just owning the GPUs locally, especially if you don't pay the electricity because your university will pay for it. To download the data, there are kind of two ways to do it. One is to go from Earth Engine to Google Cloud and then download from the cloud to local machines, which they will charge you for, both for sort of like storage and the bandwidth. The other option is to go from Earth Engine to Google Drive and then to local machines, which is free but slow. If you want to do it, it's actually relatively easy. Like Earth Engine, they have a Python API to access the data. And as you can see, this is more or less the code that you need to download stuff from Earth Engine. So you just import the Earth Engine module. Then you sort of choose the image collection corresponding to MODIS. You filter out a rectangle, or sort of like an area that you care about. You filter a date, sort of like a time range that you care about. And then you basically ask Earth Engine to export the images to Drive on either, say, Google Drive or on Google Cloud. And that's sort of more or less what you need to do it. If you do it that way, it's going to be extremely slow. So if you are planning to download stuff from Earth Engine, I recommend you to check out some of the code on our GitHub. We did a lot of hacking to make it faster, just by stacking together images and then downloading them and then unpacking them. And so you might know, instead of redoing all the coding yourself, you might as well just use our codes there. It's going to make your life a lot easier. But sort of it's not too bad to get access to the data. Now, once you have the data, you have a bunch of images that might look like this. And the question, of course, is, well, what do you do with them? How to extract something useful from these images? And this is where we go to the sort of like deep learning part of the talk. In the last few years, there has been a lot of progress in computer vision, machine learning, on basically developing techniques that can automatically understand visual data, so images, videos, stuff like that. And there has been really a lot of progress. I think I have a plot here showing the accuracy rate on the ImageNet classification challenge, which is kind of like the standard benchmark in the computer vision community, where you're trying to recognize images and sort of like classify them into 1,000 different classes. So it's a relatively hard problem. Like even humans don't get 100% accuracy. Like you might need to recognize different breeds of dogs that they more or less look the same. So it's a very, very challenging problem. And here you can see the accuracy rate as a function of time. And you can see that around 2012, there was like a big performance improvement. We go from the black line to the green one, and that's where kind of deep learning methods were shown to lead to these massive improvements on image classification problems in the literature. So you can see that in 2012, there's a big gap in the accuracy. Like there is not like these small marginal improvements that you typically see, where people keep improving the methods a little bit. There's this drastic improvement there in 2012, thanks to the use of deep learning methods. And and these, with the latest kind of deep neural networks, we are getting performances that are better than what humans can do on this kind of classification task. So I guess, okay, here I have another graph showing sort of the error rate, how it's going down. And again, you see sort of like the big gap around 2012 when deep learning methods came in. And that's kind of what I believe is really enabling a lot of exciting applications, combined with this new remote sensing data that is becoming available today. We have new data, it's getting better and better, cheaper and cheaper. have new methods that we can use at scale to understand what is going on in these images. And that is really opening up a lot of exciting opportunities for, again, going from cheap data that you can get that is updated frequently to expensive outcomes that you might want to predict, whether it's ecological, whether it's the social sciences, you care about predicting poverty or understand agricultural systems. There's a lot of stuff that I think, a lot of low-hanging fruits in this space. So a lot of stuff that can be done by applying these kind of techniques to that data. So what I'm going to do, the plan here is to, how much time do I have? Half an hour? Okay, perfect. So maybe I'll spend a little bit of time going over what is deep learning about. How many of you know about deep learning and how it works? Not all of you? Okay, so I'll go over it briefly. The idea here is that, this is a figure from Ian showing how essentially the idea of deep learning is that we have this high-dimensional input data, maybe an image with lots of pixels, and the typical approach was to try to hand design some features that might be useful for your classification problem or regression problem, and then use machine learning to figure out how to map these features to the output you care about. Deep learning is changing that by saying, well, let's try to automatically learn what kind of features are useful for the task that you're trying to solve. So the idea is that you have this modular approach, you have this high-dimensional input, which is maybe an image, you have an output, which is the thing you're trying to predict, and you're trying to learn this mapping, very complex mapping, maybe identifying if there is a forest fire in this image, or trying to regress how rich or poor an area is, or things like that. And the idea is that instead of trying to go directly from X to Y, what we're going to do is we're going to try to apply some transformations to the data, some simple transformations that will slowly make the problem easier and easier until eventually we are going to be able to lower the dimensionality of the data to the and sort of extract the relevant features that we can use to make our predictions. So the whole idea is this modular approach where we're going to apply a bunch of transformations to the data sequentially until we manage to transform it into a form that is easy and suitable for regression or classification. So the simplest kind of transformation that you can do is you can maybe apply a linear transformation to your inputs. So you have your input X, which is maybe an image, and then you apply a linear transformation, you multiply it by some matrix, and then you add some linear term. Then you're going to get some other variable that we're going to call Q. And then maybe you apply some kind of nonlinearity, maybe something like a sigmoid or a ReLU or something. And then you're going to get another variable R, and then you're going to apply another transformation, maybe another linear transformation, and another nonlinearity. You keep doing that until you get a new variable U, and then you define some kind of cost function that says that U should be close to the desired output for that particular X. And the idea is that these transformations, these linear transformations, are going to be flexible in the sense that they are parameterized by these parameters that I'm showing in red. So this matrix W and this bias B. And the idea is that by changing these parameters, if these transformations are sufficiently flexible, you might be able to do interesting transformations to the data. You might learn how to maybe map an image to a representation that is much more suitable for classification or regression. And so here maybe a cost function could be something like an L2 loss, like a squared loss that compares the output, the desired output for that particular input with whatever comes out after applying this sequence of transformations. You take U, which is the desired output, you subtract you take Y, which is the desired output, you subtract U, which is what comes out from your network, and then you square it, and you want this to be small. And of course, because we know that U is actually a simple transformation of T, then you can substitute for U, you can substitute W3 times T plus B3, and now we are writing the loss, the cost, as a function of T. And you can keep on rolling this recursion. You can write it as we know that T is just sigma applied to S, and then we know that S is just W2R plus B2, and you can sort of keep on rolling this until it becomes a function of the input, the output, and all the parameters in your network. So all the W's and all the B's. And then the idea is that, basically we have some inputs, we have some outputs, maybe some images, some outputs that you're trying to predict for those images. And depending on how you choose your parameters, your W's and your B's, you're going to get different functions that map input to outputs. Maybe some are bad, like this one. It doesn't quite match, the inputs don't quite match the outputs. So you can sort of measure how far your predictions are. You're going to get a cost. And maybe this one is not a good model. And maybe this one, for a different choice of the parameters, is a much better fit to the data. Maybe the cost is lower. And so the idea is that we're going to start with some random choice for the parameters, and we're going to update them so that it becomes better and better, reduces the cost, and then sort of like the inputs match the desired output better and better. So this is sort of like an animation of how this works. This is a simple example. You have two inputs, two outputs. You can see as you change the parameters in your network, the model changes, so the green curve changes, the way in which you map inputs to output changes, and sort of like you can see on the right, the loss surface, so you can see what's the cost as a function of the parameters that you can tune. And so what you can do is you can start somewhere, like up there, maybe at the beginning here, up in the red area, and then you see, okay, this is not doing very well. You can compute a gradient of the cost and figure out in which direction should I change my parameters so that I can bring the cost down. And then you can follow the gradient and you start going down until you reach some kind of local optimum down in that valley, which means that you're doing pretty well at predicting your outputs from your inputs. And so this is sort of like standard gradient descent. Kind of, I think the key idea here is that we can compute the gradient in an efficient way in this kind of modular architectures using essentially chain rule. The idea is that we want to compute how does the cost change as I change my parameters in the network, so W1, W2, W3, 4, and 5. How can we do that? We can use chain rule. You can figure out the first thing you can figure out is how does the cost change as I change the last variable u. And that's hopefully something easy to change, because if the cost is just to compute, because if the cost is just some kind of squared loss, then that's sort of like a trivial thing to compute. Now you can try to figure out how does the cost change as a function of t. Well, you can basically use chain rule, and you can say, well, the cost will change as a function of t. Well, it's basically you can figure out how does the cost change as a function of u, and then how does u change as a function of t. You can sort of see even formally that du cancels, and sort of you get the right thing. And now the thing is that we've already computed dc over du, how the cost changes as a function of u, and so you can use that information to figure out how the cost changes as a function of t. And then now here is where sort of like the interesting part comes in. We know that u is a simple function of t. It's just this f function, which depends on t and some parameters. And so all we need in order to figure out dc to dt over dt is just to basically what we computed before, and we need to be able to differentiate this function f as a function of t, as a function of the input. If the function f is simple, then you can do this. And then you keep going, push this computation backwards until you get to at the beginning of the network. Now what we really care about is how the cost changes as a function of the weights. And again, we can use this stuff that we just computed to estimate these gradients efficiently. The idea is that we can compute how the cost changes as a function of W5 by saying, well, let's see how the cost changes as a function of u, and then check how u changes as a function of W5. And again, we know that u is a simple function of W5, because we know that u is just f applied to t, is just a function of t and W5. So all you need to compute how c depends on W5 is how c depends on u, which you have up here. And then you need to figure out how to compute this derivative, the gradient basically of f as a function of W5, which hopefully is something simple. And now you can sort of keep doing that, going backwards again. You can figure out the gradient with respect to W4 by figuring out how c changes as a function of t, and how t changes as a function of w4. And that's something we've already computed before in this pass. And so sort of you can figure out the gradient efficiently that way. All you need essentially is a way to compute gradients of these building blocks. And then this algorithm will compute the gradient of the whole network automatically for you. And so what you can do is you can define some modules for which you can, that are sort of like natural, like linear operators or like sigmoids or ReLUs, whatever. And then you just need to figure out a way to compute derivatives of these simple building blocks. And then the algorithm we showed before will allow you to compute derivatives of the whole thing. And so even just sort of like, that's kind of the idea. It's actually, there are a lot of frameworks available today to do this. This is how you would build such a model in TensorFlow. So it's actually, very few lines of code. They're making it very, very easy to do this kind of stuff. Say we have some input x, and we want, first of all, apply some linear transformation. So you would use these two operations here. You would take x, do matrix multiplication with w1, and then you do an addition with b1. Then maybe you apply this linear, this ReLU here. You apply it here. You apply this transformation to layer 1 to get hidden 1. And then you do another maybe multiplication. And then maybe you define a cost function here. And then basically that's all you need to do. That's how you define this modular architecture, by stacking together a bunch of pieces. And then essentially you can just call this optimizer, and it will compute all the gradients for you. It will apply them, and it will optimize the cost function for you, essentially. So it's relatively straightforward to do. All that you need really is an architecture. The idea is that these transformations will basically extract features from the original high-dimensional inputs, and sort of it will learn how to extract features. Maybe the early layers will extract simple features like edges or corners or stuff like that. And then the layers that will follow will use this information extracted by the lower layers and will extract more higher level features like maybe part objects, stuff like parts of objects and stuff like that. And they will be combined together. Maybe you can, they will learn object detectors, and then when you have object detectors, you can sort of, it's going to be relatively easy to solve your classification or regression problem. And so maybe a typical architecture, if you're dealing with images, we'll use a special type of modules based on convolutions. Well, the idea is that you're going to start with your image. Maybe you apply some kind of normalization, like subtracting the mean or something like that. Then you apply a bunch of filters, which are learnable. So it's something that you can tune the parameters of these filters to find the kind of things that are useful for your specific application. Remember, everything is just a way of defining a complex parameterized function, and then you can sort of learn the parameters in order to solve the task that you care about. So maybe you start from your original image, and then you compute, you apply, in this case, like 6 filters, by sort of convolving the image with a simple 5x5 filter, and then that will compute 6 images that corresponds to the activation of these filters on the original image. Then you apply more transformations and then sort of like stack them together, and then at the end you're left with a 100-dimensional kind of feature vector here that will be used to solve the classification problem that you care about. So you stack together all these things, and then the automatic differentiation part will take care of computing the gradients, and then you will sort of try to figure out what are the parameters of these transformations that will make the whole system solve the task that you care about. And that's essentially how these networks are built. And it turns out that they work extremely well on vision and also other sort of like especially speech and audio signals. Indeed, it turns out that this transformation end up extracting features that are useful for the downstream classification or regression tasks that you care about. Sort of lower layers will identify features like edges, corners, stuff like that. Then there will be transformation here that takes the output of these low-level feature detectors, and will construct more higher-level features. Maybe parts of we'll try to detect parts of objects in the image, stuff like that. Then those will be combined into higher-level features, and so on, until you sort of use them to do the classification problem you care about. And that's essentially how these things work. The classic way you would approach the problem is you would use an existing network and an existing architecture. Here are a few of the popular ones. These are massive networks. They might have maybe 50, 100, 150 layers. So very large networks with even hundreds of millions of parameters. And what this means is that if you want to train them, you typically need a lot of data. In order to figure out what's the best way to set all of these parameters, you're going to need a lot of training data. And so that brings us to sort of like, how do we apply these problems in this context where, unfortunately, the kind of things we want to predict are typically expensive to measure, which means that getting the training data is not going to be easy. And that's kind of the reason we're building these systems in the first place, is because this stuff on the right is expensive to measure. It's hard to get the labels. And so we want to still kind of apply these ideas. So how do we do it? And how much time do I have? Perfect. So what I'll tell you about is a few ways that we've been able to deal with this data scarcity, the fact that you can't really train these systems end-to-end, sort of like take your remote sensing data, predict the things you care about, because typically you don't have enough data to do it because the things you care about are expensive to measure. And so what I'll tell you about is a couple of ways in which we've dealt with that in the context of two applications, poverty mapping and trying to sort of understand food security issues with agricultural monitoring. So the first project is about predicting poverty in developing countries. It turns out that, well, we know it's the #1 goal in that list from the United Nations. It's unfortunately one of the problems for which we have extremely poor data. Here you can see a map of the African continent, and this map is showing for each country the availability of nationally representative surveys on consumption and income and asset in the decade from 2000 to 2010. And you can see that a lot of the countries are white, meaning that there is no nationally representative survey for that country for that entire decade. And so as you can imagine, that's kind of disappointing, because if we don't have this kind of data, it's very hard to say, figure out, are we making progress toward this goal of ending extreme poverty? Are policies working or not? How do we, even operationally, like how do we help NGOs to go and help the people that need help the most? It's all very, very hard to do if we don't have good data on where poor people live. Now, on the other hand, as we said before, there's a lot of remote sensing data that is available globally, and so it's a natural thing to try to do to predict these kind of poverty estimates that policymakers and researchers and NGOs care a lot about using this remote sensing data. And this is something we had a paper in Science last year that I'm going to tell you about. So the problem is that, as I said, there is a data gap. You cannot train end-to-end from images to poverty measures because we don't have enough labels. The whole point of doing this project and working on this is that we don't have data on poverty. So one thing you can do is you can try to do transfer learning. You can come up with a proxy task that is kind of related to the one you care about, but for which you have a lot of data. And the idea is that by training a model to go from A to B, you're going to learn something useful about the original task, going from A to C, and then you can use what you've learned to help you solve the original problem. And here we used, in the context of poverty, we used the nighttime lights as a proxy for economic development. So here you can see an image of the Earth, a part of the world, taken at night by satellites. It turns out that they take images both during day and during night. And can anybody guess where this image was taken? Korea, yeah, somebody got it, yeah. So you can see, I mean, it's hard to guess because it looks like almost looks like an island, but it's not an island. It's just that there is North Korea there, and it's completely dark at night. And so you can clearly see that this proxy will, that sort of like nighttime light, the amount of nighttime light is going to provide some information about how economically developed a country is. And so the idea was to, the good news is that we have essentially an infinite amount of labels on the amount of nighttime light intensity, because these satellites, they keep basically taking images both during day and during night. So what we can do is we can set up this task where we want to predict for each location. We can take the image during day and we can try to predict how much nighttime light you're going to see at that location during night. This is a task for which we have essentially an infinite amount of data. And so we can use the latest deep learning advances to try to solve this problem. And the idea is that if you can solve this, hopefully the network will learn to identify features that are also predictive of other things we care about. Because you sort of need to figure out which areas are people live in, which areas are just sort of like like desert or like a forest or something like that. And so the network will have to understand something about the visual cues that are present in these images. So that's what we did. We trained. We have several of these models, like sort of like one of the latest CNNs to go from this input to that output. And then what we said is, we sort of try to look at what kind of features the network discovered to solve this nighttime light prediction task. And it turns out that the network is actually learning semantically meaningful features, which was very, very surprising. So you can see here each column, basically each row. The first row is a bunch of satellite images. The middle row is the activation of some filters in the network. So each column corresponds to a different filter. And the third row is just an overlay of the first two rows. And you can see that these four filters are basically capturing semantically meaningful features. The filter on the right is sort of looking for roads. You see that it's activating on these pixels corresponding to this road. The third filter is looking for water bodies. The first two are looking for sort of like urban areas versus rural areas. If you look at higher resolution images, this is a slightly different model, but sort of it also gives you the idea of the kind of stuff the network is looking for. Here, you can see the roads and the water bodies, but you see that there is a filter that is looking for roads with traffic. One is looking for houses. We think this one is looking for tall buildings that have shadow. And the most fun one, I think, was the swimming pool ones. There is a filter that is looking for swimming pools because I guess it figured out that if there are swimming pools, then there is going to be probably a high amount of nighttime lighting in that place.
About the roads.
Yeah.
It seems to me that a properly tuned network would have lots of negative examples of roads where there was no light. So have you not, are you overfitting the light or something? How do you get the road detection to work?
Well, we didn't provide labels on the
roads in cities will have lights on them, but roads everywhere else will not.
Sure.
So why is the classifier doing one but not the other?
I guess,
like
first of all, you would imagine that it's useful for detecting parts of the world where people live versus parts of the world people don't live. Like if nobody's living there, then it's definitely going to be dark at night, and roads are going to be useful. The other thing that we know that is related to nighttime light intensity is distance to like major roads. So that's another thing that is probably.
There's a lot of negative evidence that being close to a road it doesn't predict light. So that's why I didn't understand.
So the performance on predicting light is not perfect. It's a hard problem, but I guess these features turn out to be useful for predicting this.
I think you got lucky here somehow.
Well,
The model also might be discovering roads and something else.
Sure.
Yeah.
It doesn't have to be each feature has to
Yeah, so if you could explain why the rural roads are not lighting up using something else.
That's, of course, yeah, it's combining. And we did cherry pick. Like, I'm not claiming that all the there are thousands of features, Most of them we couldn't figure out what they are doing. These are cherry-picked, that the ones that we saw that consistently, that's what this filter is looking for.
Yeah, but I think Vistra is really that explains it to me. Thank you.
You combine it at the end.
Sure, yeah.
It's learned this, but that's not the only thing.
That's not the only thing, yes. And also the way we look for features is not perfect, so it's indeed possible that the combination of two vectors corresponds to something semantically meaningful. But for me, it was exciting that we never provide a label of what a road is, or what a house is, or what a swimming pool is, but it sort of figured out by itself that these things are important for this classification task. And then what you can do once you have these filters is that you can try to build a second model that is kind of using these features for predicting various measures of poverty using the kind of limited amount of data that we have. And these are some results. You can see sort of like the predictions versus the observed measures of poverty, say in Uganda in this case. And clearly, it's far from perfect. There are just things you cannot see from the images, and there is noise in the data. But it's still getting, it can explain a lot of the variation that we see in the data. And this is sort of like better than anything that is available today, even using more invasive kind of measuring approaches like looking at CDRs, sort of like call data records of who is calling, like how people use cell phones and stuff like that. We can actually do better just looking at images. And so maybe I'll skip this part on the Gaussian process part. How much time do I have? 5 minutes. So I'll skip. This is going back to what Jan was saying before, how we'd really want to model spatial correlations here. We don't just want to make predictions independently at each location. We know that these processes are spatially and temporally, there is spatial and temporal structure here. One thing that we did was to combine these kind of ideas with Gaussian processes and sort of like use the neural network to extract features and then use the Gaussian process to explain the spatial correlation, which is still something you can train end to end. And well, you can also use to do semi-supervised learning, which is another very exciting kind of idea in this space. There is a lot of unlabeled data. You have essentially an infinite amount of satellite images. And so but there are very few labels. And so one of the key ideas in this space, I think, to make these systems work will be to figure out how to do semi-supervised learning properly. So use both the labeled and the unlabeled data. Here is one way we did it, but I'm gonna skip this and instead show you, the kind of things you can do with the system. There are a couple of images of the poverty maps that we can generate. We only require satellite images, which are available globally. They are cheap. They are updated frequently. So we have this system. You can just take a country. You download millions of images that cover the whole country, and then you feed them to the model, and it will produce these poverty maps. And we know it's not perfect, but it's reasonably good. It's very inexpensive, and it can be updated very, very, very frequently. These are a couple of other examples. Let me skip this, but anyways, just wanted to say this project got a lot of attention from Bill Gates, lots of media coverage. Recently, was selected by Scientific American as one of the 10 world-changing ideas of 2016, which was very exciting. And so we were very happy about this work. We're working with the World Bank about using these estimates in some of their programs. We recently produced a map of Somalia. That's a country where they don't have any data. They cannot send people in because they get either kidnapped or killed. And so we just recently sent them a map that we produced using our techniques. I have no way of validating the results, but I guess the bar there was low because there was nothing else, and so they were pretty happy about it. I guess, how much time do I have? Probably out of time.
Just keep on talking. It's interesting.
Okay, well. I just this part is quick. I'll just show you another application of these ideas in the context of food security. It's another big problem. Hundreds of millions of people that don't have enough to eat. several challenges that you might be interested in thinking about, tracking different kind of food security outcomes using, again, sort of unconventional cheap data sources, agricultural monitoring and forecasting. These are all very important problems. Understanding how these things tie in with climate change, increased productivity, there are lots of problems where I think AI, optimization, machine learning can play a role here. What we did was to look at crop yield predictions, whether we can predict from space how productive either maybe a state or a county or even at the field level, how productive is this particular field going to be in a particular year? Can we do this from space using remote sensing data? And this paper, we looked at, again, we used sort of like remote sensing data as an input. Here we looked at time series of images because we want to try to track the growth of the plants over time. So it's not just one image, but it's more like a video. It's a sequence of images over time. And they are fed into a similar process of sort of like a neural network plus a Gaussian process that is capturing spatial correlation. And here we looked at whether we can predict for different fields how productive they are going to be. And we looked at two crops. Here we did it in the US. That's because we have more data. We looked at two crops. We looked at soybean and corn. And so this is a problem that has been looked at before. The typical approach is that you take the remote sensing data, you extract a bunch of features that domain experts thought are predictive, like various sort of vegetation indexes, and then they build a model and they try to make predictions. And the features are handcrafted and they don't take into account spatial correlation. And what we did instead was to put in our pipeline where we automatically learn features that are going to be predictive for these kind of crop yields that we care about predicting. And here is an example. You can see, so we did this in the US for each county. What we do is we take images for that county, and then we try to see whether we can predict how the total basically soybean production for that county in a particular year. And basically as we get data from the satellite, we update our prediction for that particular year. So we make these predictions every month. And here you can see how sort of like as more data comes into the model is updating the predictions and sort of like changing whether this county is going to be productive or not. We have also some work going on making predictions at the field level. But the county level stuff is already very, very promising. We actually participated in this World Bank Big Data Innovation Challenge. We won the first prize with this project. There were like several hundred applications from all over the world. I think it was like maybe $10,000 prize that the student won. So it was pretty exciting. And the model can account for spatial correlations. And here you can see an example of how it works. So this is 2012. This is a drought year. So you see the ground truth yields for different counties. You see that they are relatively low. They are towards blue because it's a drought year, so the production was not good in that year. And you can see the predictions made by the model at different months as more data comes in. So you see that at the beginning, the model is pretty optimistic in May, and then sort of like it's still pretty optimistic. And then as more data comes in, it's adjusting the predictions. And then in September, it's already doing pretty well. And then October, it almost gets it right. Just to give you some numbers, here you can see over several years the percent error that we make on our predictions. In July, for different years, so we about a 5% error across the whole United States. USDA starts making predictions in August, and you can see that in August, USDA gets on average a 3.9% error when they make predictions. So what USDA does is they pay people to go around, call up farmers, they go take samples in the fields, and they use that to make a guess for how productive, basically how much soy will be produced in the United States, which is very important. And every time they publish these estimates, you can see the future prices that change. So it's valuable information. And you can see that our model, which is just using remote sensing data, is actually getting slightly better predictions, like 3.3% error in August. In September, we also do slightly better than USDA. And then in October, yeah, we do a little bit worse. But this is exciting because it's cheap. Again, it's scalable. We just use remote sensing data. And the hope is that we'll be able to scale it up. We're working towards applying this in developing countries where this is really needed, and maybe combine it with our poverty measures. We know that agriculture is an important part of the economy there. So we think that these kind of predictions will be fed into the poverty prediction model. And so we're pretty excited about working with these new data sources, combining it, trying to predict all sort of interesting stuff, food prices, combine it with the poverty measures and so forth. And yeah, I think I'll skip that. I think I'll end up here. And thanks for your attention. So there are companies that are providing this as a service. There are 2 companies that I'm aware of that are sort of like selling their predictions to basically hedge funds that then use that information yeah. The cartel. Yeah. Yeah.
Just wondering, is it possible to account for some errors that might happen from the remote sensing estimations of the images that you're getting? Could be some possible errors in that? Can you integrate that into these models?
Which model are you thinking about? The poverty or?
I mean, like the classification models. Is it possible to account for any errors in the images that you're using for training?
So errors in the images like NANs, those kind of things?
Yeah.
Yes, and right now we have our own pre-processing, or sort of like trying to get rid of taking medians. Like we do some pre-processing because there are all sort of like some of these sensors are actually broken, and so like physically, so you have to massage the data before you feed it into these networks. It's nothing fancy, but you cannot really use it off the shelf because there are some you need to get rid of the NANs and you need to get rid of other things that might go wrong, and we just do standard stuff, nothing fancy. But we've been thinking about whether there's a better way to do it.
Is that on the GitHub script?
Yes. Yeah.
What about like predicting land cover change or predicting development? If you looked at that?
So we are doing it right now. So we're trying to see whether we can build. We are trying to do land cover changes. We have some work on fisheries also that we're thinking about. Trying to predict a lot of stuff. Infrastructure is a big one. We think that trying to understand changes in infrastructure will be important, and there's also a lot of interest. Yeah.
How big is the false alarm rate? And like in the poverty market, like you get some large number of false alarms, like the image from the swimming pool from the developed country when you're matching to the.
So, I mean, it's a regression problem. So I guess we also have a classification where we're trying to predict above or below poverty line. And I guess there you can trade off a little bit between false positive and false negative rate. But then, yeah, the model is not perfect and it makes mistakes, both because there are things that you just cannot see from above, and because just it's not perfect. I think there's a lot of room for improvement. And also trying to understand why it's making the predictions. That's another big issue that our partners at the World Bank, they care a lot about. They want to know why we're making these predictions, and that's something we don't have a good answer to yet.
So let's thank the speaker. So now we're going to have the lightning talks. So the students that have posters for this first session, please come up. So we have preloaded your slides in a folder on the computer, and you're going to present in the order in which you're listed in the program. So when you come to the podium, just like open your presentation in the respective order. Okay, so let me see. Do you want to? And again, in the interest of time, please try to stick to 3 minutes by presentation. Again, it's supposed to be not a summary of all your work, but more as an advertisement or a teaser for people to come and talk to you at your poster. Okay, so looking forward to hearing from you.